Hooke's law is a really important concept to understand in order to understand. Hooke's law is essential to understand if you want to try and rationalize how elastic potential energy will work, the energy that's stored in a spring or elastic object. So, to understand Hooke's law, we first just have to realize that it only pertains to elastic objects. Elastic meaning objects or materials that will return to their original shape once deformed. You pull a rubber band apart, you let go, it will return to its original shape. Springs are the same way, like rubber balls, same thing. Anything that can deform but then return to its original shape after that deformation is considered to be elastic. Your muscles as well are other elastic materials. It's why we can be as athletic as we are as humans. So what in the world is Hooke's law? Well, in order to understand that, we kind of have to we have to do like a thought experiment. We have to think about something that we could perform in the classroom. If we hang some kind of spring from the ceiling, let's say, whatever the length of that spring is, we call it its resting length. So I'm going to call it xi, the initial length of this thing. So it's important to understand that we have to reference the resting length when nothing is acting on this spring or elastic body, whatever it may be. So the resting length is like the original shape. In this case, the length of the original. If we apply a force to this spring, it will stretch that spring and we will wind up with some final length of this spring. All right, so you just imagine you pull down on that spring, it extends. We have our initial resting length when nothing was acting on it. Now we have this final length after some force has been applied on it. We're going to assume that the force is just holding this in place, so everything is at rest. The important thing to note here is that if we actually measure what we call the change in the length, which is the final minus the initial, or that area that I've kind of highlighted in orange there, we can then record two pieces of information. We can record the force that we applied, as well as the resulting change in length of the spring. And that kind of will give us a coordinate that we can plot on a graph in a second. So just understand that if I apply some force, that spring will deform, go through some extension, and I can relate the force that I applied as well as the extension of that spring. Now I can do this again and again, so you'll notice here I apply a larger force, it extends even more, but I still measure that displacement of the spring from its resting length. I don't just add it on to wherever it was when I previously, in the middle part, pulled that force down. I have to apply a force and see how far from its resting length has the spring stretched. So again, I can do the same thing. I now have a larger force and a larger displacement from its resting length. And I can do this multiple times. I can do this over and over and over. And eventually I'm going to get to generate this table of the forces that I applied and the resulting deformations of that spring, how far they've stretched from the resting length under those different forces. All right, so if you just imagine that, we could get as many points as we want. Let's pull the rubber band, the spring, whatever. Let's see how far it stretches under this force, and then we'll see where we go from there. So once you have that information, once that information has been collected, we can take that information, we can take that information and we can actually start to plot it. So you can see on the side here, if you take whatever forces you applied and you plot it against the deformation from resting length, you can get this graph that looks like this. And you will find that as long as you don't stretch these springs, stretch these rubber bands so far that they are permanently deformed, that Hooke's law will apply. So you probably know what I'm talking about. If you've ever played with a slinky and you just happen to pull it too far, you stretch it too much, you let go of it, it kind of ruins the slinky. Like it won't go back to its original shape. So as long as you don't do that, you will find always, 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 you get this linear relationship. So if you put a line of best fit in there, no matter what spring, no matter what rubber band, etc., you're going to find that it has a linear relationship. And that becomes really important because that is Hooke's law. So the slope of that line for whatever spring or elastic band you're looking at, we call that slope K, which refers to what we call the spring constant, which I'll explain in a second. Spring constant because the slope is not changing, it's constant. But anyway, to find that slope, it is the change in y over the change in x. So in this case, the y variable is the force in the spring, and the x variable is literally the change in x of the spring. So if I go further on this, we can realize that K, the slope, is just the spring force over the spring extension. And if I just multiply both sides by the extension, you get Hooke's law, which is the spring force, the force in the spring, is equal to K, which is the spring constant, times delta X, how far that spring has been stretched. The spring constant is really a value that tells you about the stiffness of the spring. So if it's like a really sturdy spring that's very hard to compress or stretch, maybe like the shocks in your car, that has a very high, what we call K value, or a very high spring constant. If you've ever taken apart your mechanical pencils and you know that little spring inside, sometimes you can take that out and play around with it. It's very easy to kind of smush that between your fingers. It doesn't offer a lot of resistance. That is a very low K value. So just understand for the moment that the K value gives you an idea of how strong or how stiff this spring is. The stiffer it is, the harder it will be to compress, the more force you'll need. The lower the K value, you don't need a lot of force, and it will be very easy to deform this spring. All right, so in the next video, we'll go over a few examples. It'll probably help you understand Hooke's law a little bit more concretely. But I should, before we end, give you the final breakdown of Hooke's law. So Hooke's law, just to clarify everything, states that the spring force, the force in any spring, is equal to the spring constant multiplied by the displacement of that spring, how far you've stretched it or how far you've compressed it. And you just have to make sure that since spring force is a force, it's measured in newtons, you must always measure the displacement of the spring in meters from the rest position. And because, going back to a previous page, because the spring constant is found by dividing the spring force in newtons by the extension of the spring in meters, the spring constant is always measured in newtons per meter. So it tells you how many newtons you have to apply to this specific spring in order to stretch it 1 meter. And as long as you don't break that spring, no matter what force you apply to it, the spring constant will be constant. And that is a very powerful tool when we want to analyze springs, rubber bands, and other elastic bodies, as we will see in the next video.